Hello everybody, this is Mrs. Ewald signing in, and today we are going to be talking about matter, properties of matter, talking about also classifying matter. So to start off, please make sure that you refer to sections 3.1 to 3.4 in your textbook, pages 57 to 65, in case you need any further reference or need to make sure that you look at any other examples or anything to help you, just to help supplement with the podcast. So make sure you have that available. First thing I want to do is talk about what properties are, both physical and chemical. So a physical property can be observed without changing the identity of the substance. So for example, if I wanted to look at water, I could note that it's clear. That would be a physical property. I could also determine its density, which is 1 gram per cubic centimeter, and that would also be a physical property. If we're talking about metals, it would be whether or not it's ductile, malleable, hardness, those types of things. Then there's also chemical properties, and this is the ability of a substance to change its identity. So for example, if I'm talking about a chemical property, let's go back to the water idea, I would say that oxygen can combine with hydrogen to make water. That would be a chemical property of the oxygen and the hydrogen in order to form water in that reaction. So please make sure you separate physical versus chemical properties. Let's go through some examples of these to make sure that you are all right with that. For example, melting point. Would this be a physical or chemical property? Well, melting point, this would be physical. Why? Because we're observing this without altering the identity of the substance. Flammability, if something is flammable or not. Well, if you were to light something on fire, folks, it's going to be changing, right? So this is going to be a chemical. Density, if I wanted to get the density of gold, for example, I'm not going to be altering that at all, so this would be physical. Magnetic, to see if something or test if something is magnetic, this would also be physical. Again, it's not going to harm the substance. And then tarnishes in air. Well, if something does tarnish in air, this is going to be chemically altering it. So this would be a chemical property. All right, moving on. Physical versus chemical change. Now we are talking about changes. So physical change is changes in the form of a substance without changing its identity. So the properties of that substance will remain the same. So if I wanted to take a beaker of water and heat it up, here's my flame, sort of more or less. So if I heat this up and I let it boil, well, boiling that water is not altering the water molecules at all. That would be just a physical change, a change in phase. If I were to take ice cubes, oh, this is awful. Oh, awful. Awful. Let's erase that. If I were to take some ice cubes and just let it melt. That's nice. That worked out. This is going to be melting. Again, I'm not changing those water molecules at all. It's just a change in phase. So that would be an example of a physical change. A chemical change is changes in the identity of a substance. So the products are going to have different properties. They're going to behave differently. So if I were to take sodium and place it into water, you're going to have a pretty reactive response to that. And that is going to change the properties of the two. Also, rotting meat. I don't know if any of you have ever had the pleasure of smelling that, but there is definitely something going on chemically during that, which gives that awful, awful smell. So here are some signs then noting if a chemical change or chemical reaction too is occurring. So you're going to notice a change in color or odor while the reaction is occurring. However, don't ever confuse this with like adding just like food coloring, because food coloring does not alter the substance. I just always have that question whenever I put food coloring into water. All it's doing is just diffusing in the water, and we see a different color from it. So that would not be a chemical change. However, noting a color after a reaction because of certain indicators, you know that it's changing from an acid to a base, or its pH is changing slightly. A formation of gas. How do you know that? You're going to see bubbles. Lots of bubbles. What does that tell you? It tells you that a gas is given off. Now, we obviously can't see gas has been given off, but we could definitely see based on the bubbles that are forming that a gas is being released. Formation of a precipitate or solid. This is a big hint that a new substance has formed. And we see it resting at the bottom of our beaker or test tube. You know something's up. And then lastly, a change in heat, change in light or heat. This is a huge sign of a reaction. It's also telling you, if you have heat being released, that energy is released in the form of heat energy. So that would be a big sign of a chemical change. If you want to, go ahead onto this link. It's a YouTube link showing you elephant toothpaste, which gives you an excellent example of a chemical reaction, and watch for those signs in that clip. So you could do that on your own. Let's move on to the next thing with states of matter. And this gets into solids, liquids, and gases. So a gas is going to heat up, or a gas has lots and lots of energy, right? And you could change from one to the other. So this is also showing you those different phases of matter. So what would fit right in here then? Well, this would be a liquid. So if a liquid freezes, it forms a solid. If this heats up or boil, you will then get a gas. And then you could also slow those gases down and form a liquid. And liquids will then freeze and go back to solid. So it's a big triangle showing you how one will form into another. This visual here, first thing I want to mention is that there is a big misconception with this visual, which is also a visual in your book to help show you solid, liquid, and gas. And it's talking about the kinetic theory. And the idea is that if you have a solid with these molecules, molecules are constantly moving. And they're going to want to move away from each other. But when they're a solid, they make this really nice lattice structure. But if I, put in some more energy into this, well, now those molecules are going to want to move further and further and further away. They're really, really excited and they're bouncing off the wall. They're going to want to separate from each other. So bonds are going to break, they're going to move further apart, and then you're going to have a liquid. Now, if I excite this even more, again, based on the kinetic molecular theory, these are going to move and move and move and move until they move further and further away from each other, forming a gas. But the big misconception here is a lot of people think then when it forms a gas that you have less of them. Not true. It's just the visual trying to show you how they're moving further and further away from each other. It just doesn't do it justice. What you would actually have to see in here is the same number of all of those molecules just further away from each other. So don't ever get that confused. But solids definitely are going to have a fixed volume and a fixed shape. Liquids are going to have a fixed volume. And as far as the shape, obviously it could change based on its container. And gases do not have a fixed volume or a fixed shape. They're going to be able to take on the shape of the container, and we can also change its volume based on the pressure. So let's talk about the last thing with classification of matter. So if you were to complete this flow chart, well, really basically this is what you need to be able to make sure you can do in order to fully understand how matter is classified. So matter can be broken down. It could either be, can it be physically separated? If so, well, what will it break into? And if not, well, what will that break into? You could break it down even further and say, well, can it be chemically decomposed? Yes or no? And is the composition uniform or not? So this here provides to you a flow chart using all of the terms, making sure that you fully understand how everything is arranged. So if it can be separated, then it's going to be a mixture. If it cannot be, it will be a pure substance. Well, pure substances, they're depending on if it could be chemically decomposed or not. It can either be a compound or an element. And mixtures can be broken down based on its uniformity. So if it is uniform, it's a homogeneous mixture, a solution, which is what we're basically interested in chemistry. And if not, it's a heterogeneous mixture. So you should be able to define each one of these terms and know where everything fits. Give an example of them. For example, a compound example would be sodium chloride. An element, well, that would just be everything on the periodic table. Sodium would be an example of that. When you're talking about homogeneous versus homogeneous versus heterogeneous mixtures, again, you should be able to give examples of both and understanding what that means. Moving on. Here are examples then of pure substances. So those elements, they are composed of identical atoms. So copper wire, aluminum foil, those are everyday things which are showing you that are made of just strictly elements. Compounds are going to be composed of two or more elements in a fixed ratio. So here it's showing you the sodium chloride. And the properties differ from those of the individual elements. So when they come together and form a bond, they are changing their properties. So that would be a compound. Mixtures then could be heterogeneous or homogeneous. Notice the big differences here. So this would be not uniform in the sense that you could see what each of the parts are inside here, and versus uniform. So here, if you were to look at any one of these area of the solution, it should look identical to anywhere else. And that's how you know if something is homogeneous or heterogeneous. So as far as mixtures go, a solution is going to be homogeneous. You're going to have very small particles. The particles do not settle, so you don't have to precipitate. So a big example there would be like rubbing alcohol. That could sit on the shelf for a very, very long time, and you're never going to know what the parts are because they don't ever settle out. So your turn. Here are some examples of different mixtures or pure substances or elements. And what I want you to do is on your own think about, first of all, is it a pure substance? Is it a compound or an element? And then think about, well, is this a mixture? Is it heterogeneous or homogeneous? So take some time. Write down an answer for each one of these and have that prepared for class tomorrow. I would also like for you on your own to make a concept map using the terms that we just went through and put all of this together. The only thing we really did not mention too much is the law of conservation of mass, but that is in your book. So go through, make sure you look at everything, write down lots of questions if you need to, and we will discuss this in class as well as do some more examples with classifying. So this is me, Mrs. Ewald, signing out, and happy classifying.